Bismillahir Rahmanir Rahim. Assalamu alaikum. I am Dr. Amjad Ali, and I am just here to introduce you my article, Demystifying ANN with Mathematical and Graphical Insights. So, in this article, we have presented the basic working of artificial neural networks, their usage, and especially many of their mechanisms and derivations, and some example codes and pseudocode as well. So, in the introduction part, we have just mentioned the basic history, the basic terminology of artificial neural network somehow, and we have compared it with the deep learning, with the machine learning. What is the difference between ordinary machine learning algorithms and deep learning or neural network algorithms? So, what is the main difference? We have elaborated that feature extraction is automatic in deep learning or neural network algorithms. So after having some discussion on historical background, we have presented the layout, or you can say the list of contents of different sections in this article. Next, section 2 is schematic structure of simple artificial neural networks. So this is the schematic structure we have elaborated in a figure like this. Then the linear combination of weights and inputs to produce next neuron. In fact, first of all, it will be pre-activated neuron. Then after application of the activation function, it will become activated neuron. Then after this, a multi-layer perceptron MLP or simple feed forward neural network. We have explained this. What is input layer, output layer, what are hidden layers? We have given them labels, you can say names or titles and indices as well. We have properly elaborated from which space this input or weight belongs, what is the size of the space. Obviously, we are taking real valued data. So we have given notation for every relevant vector and matrix. Then we move on to forward pass, finding neuron values in an artificial neural network. So step one is finding the dot product of the input values and weights. So this is a figure we have specially prepared for this to elaborate what are the you can say notations for different neurons and layers after having pre-activated value, and in fact not the pre-activated value, just to make the pre-activated value, first we have the linear combination, then we add bias into that and then apply the activation function, then we get the activated neuron. So here we have listed several well-known activation functions and their derivatives with their graphs and with their description as well, obviously formula of the function and its derivative as well, the expression for that. Next we have presented how we reach at the output layer, layer by layer. Then what is cost function, what are the famous cost function available in literature, we have mentioned that in a table. Then after having completed the discussion of forward pass and loss function, now we are going to drive how to find the derivative of the loss function with respect to the model parameters. Those are weights and biases. So we derive the expressions for the gradients using the backpropagation. So we have so much detail on the backpropagation algorithm, how it works. So we have elaborated it completely. We have given so much detail in that. So if anyone is curious how we get expression for the derivatives of the cost function with respect to the weights and biases of any of the previous layers, then we have developed this one. So this is the figure, one of the figures which is elaborating how the derivative approach works. We have suppose this is a very small example network. So it has one input and one output layer and two hidden layers. So how we will compute the cost function derivatives at each of the neurons of the hidden layer and the output layer. So we have elaborated that for any particular parameter, what will be the path of chains of derivative to compute the cost function derivative. So obviously, if it is in the earlier layer, it will involve all of the subsequent following parameters or and neurons which appear on the way on the path towards the output layer. So we will see all possibilities from that particular connection to the output layer. Learning of the neural network model through optimization. We have next elaborated this. What is mean by optimization, how an optimization algorithm works. Then we have also discussed along with the gradient descent method what are the three approaches like uh, batch gradient or stochastic gradient descent method or mini batch gradient descent method. We have mentioned expressions for that, and interestingly we have tried our level best. First of all, we give the general expression, and with the change in the value of this m, the number of instances in that particular mini batch, if we specify the value of m as n or 1 or something else in between m and capital N, we will get these three forms of gradient descent methods respectively. So this is quite a simplification of expressions. Then we will use the derivative in the parameter updation formula. What is alpha and how the error draws for these three different approaches. What if alpha is too high or just right or too low? We have elaborated this. And if epochs or iteration count increases, then what is the effect of alpha, if it is whether it is very high, low, medium, or a moderate value. So what we see in the good learning rate, the speed is not extremely fast, but we reach but we achieve the lowest cost function value because it keeps dropping. So again, there is a comparison of the three approaches. After this, once the overall you can say forward pass and then uh, back propagation and then updation of the parameters have been done, then we can say that we have this schematic diagram of the neural network process. Then a specialty of this article is one of the specialties is that we have taken an example of very small data set just to show how these working, how these computations can work. So we have gone through this normalization, then we designed a network architecture, and we labeled relevant neurons, pre-activation, post-activation values, layer numbering, neuron labels, and then notation for the parameters from which particular link it belongs. Then we have worked out the calculation by hand manually to elaborate what is happening over there. Then the cost function computation, and then it comes to the learning phase. And next we have this how we find the derivative of the cost function with respect to the parameters for a particular parameter, just like this. What will be the path of the link towards the output layer, and how the chain rule is working? We have elaborated this for every possibility. Next, we update the parameters. After this, having the concept of all this, now we are able to, now we are in a position to design a vectorized implementation of the algorithm. Means we can say that we can design the pseudocode for this. We can express the algorithm as pseudocode. Then here you can see we are defining the variables and what a particular variable mean. We have elaborated their structure, their formulas, their expressions, their notations in detail. Then here comes the procedure. We are initializing relevant variables, declaring relevant variables. Then we are defining the functions for the activation function and cost function, several options. Then here comes the procedure. This is the elemental procedure in which we have used explicit loops. After this, we have presented vectorized implementation in matrix form, in which many of the loops are hidden within the vectorized operation. Those are implicit. Now we are taking a test case of stock exchange data for a company, and obviously it is time series data, but still we are using simple artificial neural network for it. So this is the code. This is you can say the manual code without using any framework like PyTorch or TensorFlow or JAX or Paddle. We are just using NumPy in this. And obviously here we are not making hyperparameter tuning just to get some results and what is the cost function after executing this code. Then we present the a similar implementation of the same idea using the TensorFlow, and we get very much similar results on execution. Then practical considerations for improved neural network training. Issues in the training the neural networks. So what are the issues like overfitting, underfitting, vanishing, and exploding gradients, high computational cost, slow convergence for optimization, data collection. After having mentioned these issues, now how we address similar issues or these issues in different stages. So first of all is the data collection or data generation. What we do here, we are discussing here. Then data pre-processing and feature engineering part is there, and designing the neural network architecture next. In this, what we actually do and what kind of factor we should keep into mind in our mind while designing the architecture. Initialization techniques, how we initialize the parameters, zero initialization, random initialization, Glorot initialization, He initialization, Lacan initialization. So there are several, we have mentioned several approaches, hyperparameter tuning and model validation. What is its concept? What are hyperparameters and how we tune them? And we present holdout validation and k-fold cross validation techniques for the ANN. So we introduce relevant terminology as well. What is training error? What is generalization error? So this is one of the specialties of the article that we are mentioning. We are elaborating through a special illustration. What is the concept of model building and testing? And this is here. This is where we perform holdout validation. Next, we found such a table of training error and validation error, and we identify whether it is overfitting or underfitting or both. K-fold cross validation technique. Again, we have very good elaboration for it. So it is a custom made illustration. Next, a regularization, how we control the overfitting and several other issues. So we have mentioned different sources, different texts for consultation, and still we uh, are mentioning several regularization techniques here: L2 regularization, L1 regularization, dropout regularization, early stopping the relevant graphs to identify the situation, data augmentation, data set augmentation. Still, it is being treated as a regularization technique, enhancing robustness with variations, challenges, and limitations of these uh, data augmentation. Next, batch normalization of each layer. So we can perform batch normalization to address various issues related to neural networks. Some advanced gradient descent strategies for efficient training. So this is one of the special topics of this article that we are presenting. Previously, we just presented one algorithm, that is gradient descent, simple algorithm. You can say vanilla. Then now we are presenting gradient descent with momentum, its expressions, gradient descent with Nesterov, momentum, gradient descent with adaptive learning rates. There is another kind of approaches in which the learning rate is adaptive. One is ADA-grade, RMS prop, the root mean square propagation technique, ADA delta, the adaptive delta technique, the adaptive moment estimation technique, the famous Adam algorithm. We have presented its mechanism. So we have discussed several well-known and famous optimization techniques for the parameter training, enhancing the model performance for the test case. Now, as mentioned, we have used a very simple test case without hyperparameter tuning. Now we will enhance its performance through hyperparameter tuning. So here we take various uh, upgradations in it. In fact, we change the algorithm of optimization, we change the network architecture. Perhaps we have here, yes, here we have make minimal changes. We have changed the size of mini batch, and we have changed the optimization algorithm. In fact, we have make very few hyperparameter changings. Still, we are able to get a very good result, and we have presented that in a special. So after prediction, what we get is the error is very low. So you can see that training loss and validation loss both are very much similar. So it means there is no overfitting as such. And because it is very near to zero, so there is no underfitting as well. So this is what we are getting for the test data. So below one is the true value, and the red graph is showing the predictions. So obviously, we are not claiming the best results at this moment, because for this time series analysis, we can use some different architecture, or whatever our architecture is that we can perform further hyperparameter tuning. So here we can, it was targeted to mention that previously when we were not using any kind of hyperparameter tuning, we just randomly choose some values of hyperparameters, then the error was very high. But now you can see the error for the prediction is quite low as compared to what we have previously. Previously it was like 30 plus, now it is around 4 and 6. So this is the conclusion that whatever we have seen in this document, what was the purpose of this document, and finally the acknowledgements and the references. So basically the purpose of this video is that just to have this article in my video. Later on, I will prepare well planned explanation of this article. Hopefully, I plan to do so. Thank you very much.